Hello, welcome back to another video. So in this video, we're getting into sequences in series as part of the IB Math AA-SL curriculum. Anyway, let's start today by defining sequences. So what's a sequence? Well, a sequence of numbers is something that looks like this. 2, 4, 6, 8. This is a sequence of numbers. We have 2, 4, 6, and 8 in what we would call ascending order. More formally, a sequence is a list of numbers that are written in either descending or ascending order, and they follow a specific rule. Like in the example here, 2, 4, 6, and 8. It's first we identified that it's in ascending order. Now let's look for the pattern or the so-called rule. What rule does it follow? So let's see, from 2 to 4, how could I get from 2 to 4? I can add 2. From 4 to 6, I can add 2 because 4 plus 2 is 6. 6 to 8, I can add 2. So this so-called rule is that we add 2 to get from the previous number to the next number. We have to add 2. That's the sort of rule that we found. Now there are two types of sequences. Here, there is what we would call, so we have our sequence. There is what we would call a finite and an infinite. And so a finite sequence it has a fixed number of numbers or a fixed number of terms, like the sequence 2, 4, 6, 8. This sequence in itself is a finite sequence. There is a fixed number of terms, 2, 4, 6, and 8. An infinite sequence is, well, from the name, it goes on forever. Infinite. It doesn't end. There's an infinite number of terms. So if I were to write 2, 4, 6, 8, ... These three dots indicate that it's going on forever. This is an infinite sequence. Very simple. Very fundamental. Okay, so let's say we have a finite sequence. 2, 4, 6, 8. Again, the same sequence. By terms, we're referring to these. 2 is one term, 4 is another term, 6 is another term, 8 is another term. These are the terms of the sequence. Mathematically or algebraically, we would refer to these terms using variables, okay, to do mathematics. So we could refer to this first term as u sub 1, u1. And then the second term would be u2, third u3, fourth u4. You see the pattern. Obviously the variable doesn't matter and all that stuff. But u is conventionally used, this letter u here. So we do this because we want to do mathematics with these sequences, and we often come up with a general formula, so sort of a general expression or a formula that we could plug numbers into to describe our sequence. That would give us each term of our sequence. More on that in a bit, but I wanted to mention that. And we refer to this general formula as un for an arbitrary term. N could be the first term, second term, third term, fourth term. As I said, we generate terms using this general formula. Now all that language seems abstract, but we're going to get into it. Under sequences, we also have two general types of sequences. We have what is known as an arithmetic arithmetic sequence and a geometric sequence. And for today, we're going to get a bit into the arithmetic sequence. So an arithmetic sequence is just like what we saw in our beginning example. In an arithmetic sequence, what happens is that we add the same number to each term to get to the next number. So we add, for the first term, we add 2, we get to the next term. From this second term to get to the third term, we add 2 again, the same number, and so on. And we could also have descending order. So we could go from 8, 6, 4, 2. Instead, we'd be subtracting from each term, but the same number. Now let's define these aspects of an arithmetic sequence, again, to do mathematics. So again, we have our same finite sequence here. What's 2? 2 is the first term, which we'll call u1. 4 is the second term, which we'll call u2. 6 is the third term, which we'll call u3. 8 is the fourth term, which we will call u4. And the pattern that we found, or the rule, the so-called rule, specific rule that this sequence follows, and in an arithmetic sequence, is that we add the same number to each term. So u1, or 2, the first term, we would add plus 2 to get to u2, which is 4. And then to get from the u2, the second term, to the third term, we add 2 again. And to get from u3 to u4, which here we're considering our final term, we add 2 again. So clearly we have an arithmetic sequence. Give an algebraic name or an algebraic meaning to this rule, or the 2 that we're adding. We're gonna call this our common difference. And our common difference, D. D is what we call our common difference. Why is it a common difference? Because we have the same, because it's a difference. The difference between two numbers. So if we look here, between 4 and 2, the difference is 2, because 4 minus 2 is 2. 6 and 4, the difference is 2. 6 minus 4 is 2. 8 and 6, 8 minus 6 is 2. That's the common difference. One is 2 greater than the other. So 4 is 2 plus 2. 6 is 4 plus 2. 8 is 6 plus 2. That's the pattern again. So this D here is what we'll call our common difference. And when D is positive, like in our case here, we have D is equal to 2. D is our common difference. The difference between each term is 2. And we go from one term to another by plus 2. So D is 2. It's positive. 2 is greater than 0. It means that our sequence is increasing. We have an increasing arithmetic sequence. And we see it. 2, 4, 6, 8, it's increasing. If D was less than 0, meaning we'd have a negative common difference. So let's say 2 in our case here was negative 2 instead. Well, that would just mean we have a decreasing sequence, because we would be decreasing. We would be going from 2, minus 2, minus 2, minus 2 would be decreasing. Now let's write this in more abstract, or in a more generalized way. Okay? So we found an algebraic way of writing our terms using u with the number indicating which term it is. So u3 is our third term, u4 is our fourth term, which is 8 and 6, and so on. So now using this, let's find a general formula for our sequence. So I wrote out our terms over here, u1, u2, u3, u4, and our terms are separated by a common difference of 2. So D equals 2, our common difference. Let's write this in a more generalized way. So instead of 2, 4, 6, and 8, I'm going to write u1, u2, u3, u4. u1. Now, what is u2? u2 is 4. What's another way we could write u2? Well, we could write it as u1 plus d. Why is that? Well, we know that u1, again, is 2. D is 2. These are common difference. And so, we have 2, 4. 2 plus 2 is 4. We're going from our first term. Our second term is the first term plus d, plus 2, because we're increasing by 2. That makes sense. Let's continue. How can I go from how can I rewrite the third term in terms of u1, in terms of our first term u1? Well, to go from u1 to u3, or looking back at our original sequence, from 2 to 6, we have to add 2 twice. From 2 to 6, the difference is 4. Because we're going plus 2 and another plus 2 to go from 2 to 6. So we're going 2 times 2. 2 times 2. And what is 2? 2 is our common difference, so we could write 2 times d. Great. So to go from our first term to our third term, writing it in terms of u1, we could say that it is u1 plus 2 times d. u1 again being 2, d being 2 as well. Finally, our final term, u4. Try it out for yourself. Pause the video and see if you can work it out. So u4, let's go back to our sequence. Our sequence is going to help us here again. To write our fourth and final term in our sequence in terms of u1 and d. So to go from u1, the first term, which is 2, to the final fourth term, which is 8, we have to add 2, add 2, add 2, and we finally arrive here. So we're adding 2 3 times. 3 times 2. And this is 6. And if we find the difference between 8 and 2, it's 8 minus 2. The difference between the fourth term and the first term. 8 minus 2, 6. Which is again 3 times 2. And we know that 2 is d. So 3 times d. 3 times the common difference will get us from 2 to 8. So let's write that out. 3 times the common difference. So when we add 3 times the common difference, we go from u1 to our fourth term. Great! See, we found a generalized version of our sequence in a more algebraic way. What do we notice here? We notice they're all written in terms of u1 and the common difference. So it's all about our first term and the common difference. And the common difference, we're just multiplying by certain numbers as we go further into the sequence. Because you start out at u1, the second term is u1 plus d, as seen here. The third term is u1 plus 2 times d, because we're going plus d, plus d. Finally, in the fourth term, we're going another plus d. So going from the first term to the fourth term, we're adding d 3 times. So now if we go back to our original sequence and we find the difference between the second term and the first term. Second term is 4, first term is 1. We get the common difference. We get the difference between them. 2. Makes sense. And 2 we know is d, the common difference again. In our algebraic version of this sequence, if we take the second term, which is u1 plus d, and then find the difference between it and the first term, which is just u1, we see that we get d, because u1 minus u1 is just 0, and we get d, which again is the common difference here. Now, before I end this video, I wanna write our sequence. I wanna deduce something from our sequence to ready you for the next video. Okay, I wanna deduce something else from this generalized version of our sequence up here. So we have our first term, our second term, our third term, our fourth term, first term, second term is equal to this, third term is equal to this, fourth term is equal to this. But up here, we were just writing it all in terms of U1 and D to show you really how that sequence worked, how the sequence works. I'm going to write these findings here. So we found that U1 obviously is U1, U2 is equal to U1 plus D. When we add plus D, we get to U2. We can write it in this way, as we've already done. Anyway, I'm going to continue. U3 is equal to, in terms of U1, plus 2D, because we add D and then another D, we get 2D. And the same goes for U4, the same logic, but we would have 3D. So we've written U2 in terms of U1, U3 in terms of U1, U4 in terms of U1. So that means that we could find a general formula in terms of U1 and a common difference. A general formula that would give us any term, any nth term. For instance, back here, for the fourth term, we have this formula in terms of U1 and D. For the third term, we also have this. For the second term, we also have it. First term, well, that's quite obvious. Okay, let's pick some random expression or equation or formula here. U4 is equal to U1 plus 3D. U4 minus U1 is equal to 3D. Makes sense. To go from the first term to the fourth term, the difference between that will be 3 common differences. 3 times the common difference. So that makes sense, as I've shown in our sequence previously. But notice something special here. If we look closely at the numbers down here indicating which terms we're dealing with, so we're dealing with the fourth term and the first term. And what's 4 minus 1? The difference between that, the fourth term and the first term, is again 3 common differences. 4 minus 1 is 3. To go from first term to fourth term, we go by 3 common differences. As again I've shown in the sequence previously. So in a generalized way, we could just say U n for any term, any nth term, could be the 5th, the 6th, the 7th, the 8th, the 1st, is equal to, in terms of U1 and D, U1 plus n minus 1 times D. And we found our general formula. Let's take another one of these expressions we've written out here and see. And what I mean by general here is that you put in any n for any term you want to find, and you would get that number. So say I wanted the 6th term. U6 is equal to U1 plus 6 minus 1, because we picked n is equal to 6, 6th term, times D. And this is equal to U1 plus 5D. So U6 is equal to U1 plus 5D. To go to U6, we go from the first term and add 5 common differences to get to the 6th term, whatever it is. Makes sense, and I've exemplified this in the sequence. We've seen how this works in an actual sequence in terms of common differences. Okay, now this isn't a formal proof. We didn't do a formal proof of the formula, or of a general formula for an arithmetic sequence. But we used, we deduced and we arrived at a conclusion, which is this general formula. And I forgot to specify, it only works, this is for arithmetic sequences, because we're arithmetic, in an arithmetic sequence, we've learned that we add common differences. Geometric sequence is for another video. Let's do an example and see how this plays out, how this all plays out. Say we have this arithmetic sequence, or you could even call it an arithmetic progression. So say we have this arithmetic progression, and we're asked to find U12. We're asked to find U12. What's U12? Again, we use this notation to refer to terms. So what this question is basically asking is to find the 12th term in the sequence, where we have 14 as our first term, 11 as our second term, 18 as our third term. Well, we could use this general sort of formula to find the 12th term. And let's understand it a bit along the way. So our general formula for an nth term, any term, is expressed as follows. So let's forget this general formula for a bit, and let's look at our sequence here. 14 is our first term, so we know U1, it's 14, and U2 is 11, the second term. Now we're told that this is an arithmetic sequence, and in arithmetic sequence we know that to get from one term to another we add a common difference, or subtract a common difference. So let's find the difference between any two terms, okay, and we would find the common difference. So between U2 minus U1, second term minus first term, we would get D. And we know that this is equal to our second term, which is 11, minus our first term is 14. We get negative 3. So D is equal to negative 3. We have a decreasing sequence because we're subtracting. We're adding this negative common difference, which means that we're decreasing. Back to the sequence above, we add negative 3, or we subtract 3, minus 3. We see that we're going 14 minus 3 is 11, 11 minus 3 is 8, decreasing. Okay, so we found the common difference. The common difference, okay. Now U12, given the information here, how can we find U12? Well, we could use the general formula, but I want to show you how, by thinking about it, you will arrive at the general formula anyway. So U12, and let's pick any term in the sequence and see how we could get to U12. For simplicity, I'm going to pick the first term, U1. To go from the first term to this 12th term, how many common differences do we need to add? Well, 11 common differences. 11 times D. 11 times the common difference that we have. Because if we're going from 14, 11, 18, and so on and so on and so on, all the way up to U12, we would be adding this common difference 11 times. So it's 11 times this common difference we would have to add to the first term to get to our 12th term. See how I'm thinking here? We've arrived at our general formula anyway, because remember our general formula for any nth term, for any term to find any term, is as follows: n minus 1 d. And our n in this problem is 12. N is equal to 12. So up here, U12 is equal to U1 plus 12 minus 1, as in the general formula, which is equal to U1 plus 11D. The same thing, the same as we found just by thinking. So it's all about logic here. You could apply the general formula, you could neglect the general formula. Anyway, let's go on with our problem and find the 12th term. So we know U1 is 14 here. 11 times, what's D, the common difference? Well, we found the common difference that we're adding for this arithmetic sequence is negative 3. So just doing the math here, we get negative 19. So our 12th term, U12, in this sequence is negative 19. Negative 19, the 12th term, minus the first term, which is 14. First term is equal to negative 33, which is equal to 11 times negative 3. 11 times the common difference would take us from the first term to the 12th term. So finding the difference between those two is 11 times the common difference. As I just showed, we go negative d, negative d, negative d 11 times until we reach U12. Thank you for watching. I'll see you in the next video as we continue our journey through sequences. I hope we've learned something today, and I hope you understand how arithmetic sequences work. Good luck and goodbye.